Hello, I'm Dr. Vivian Lowe, and you're on VLMD Rounds, a podcast on medical science and tools to optimize your health. Now, before I start, as usual, I'd like to give a shout out to a few people. So, T. Trotter, Elizabeth De La Torre, Jonathan, and Conrad. You had all reached out to me on YouTube. Thank you so much for writing in and sending me your comments and questions. Also, B. Liba and Siranesh. I know you've been listening into the podcast. And again, thank you for writing in. And I hope you've been finding these episodes helpful. Also, Michael on LinkedIn, and you wanted to know more about the glycocalyx. I hope you found the reference to the glycobiology textbook useful. It's a massive topic, and I'm still trying to work my way around it. But once you see those proteoglycans, you can't unsee them. They're everywhere, and they're really important. Thank you for writing to me. And also Daniel, who wrote into my website. Thank you, Daniel, very much for that delightful clip on the tango lesson. I really enjoyed that very much. And I just want to say that since I've started this podcast, it's really been a joy to connect with different people all over the world who are interested in science and also in the arts, and just to hear your comments and your questions, and also to get suggestions from you on what topics I could do on the podcast. Now, if you're watching in on YouTube, you'll see I'm not in my usual setup, so that means I'm traveling again. That's always a challenge because I'm trying to manage my schedule. I still have to teach and in a bit, so I'm keeping an eye on the time. And then there's the time change, so I have to manage that as well, and all the other projects that I'm juggling. But I always enjoy doing these episodes, so I'm glad I was able to squeeze in time to make this one. Today we are going to be talking about lipoproteins, and it's going to be a part 1 episode because there's just so many aspects of lipoproteins that I'd like to get into. I thought, since I'm traveling, let's just do some of the basics today, do a little review. Those of you who are familiar with the topic, I hope you'll still maybe find some new bits here and there. I always find that sometimes when I think I know something, I go back and I look at the basics again. There's so many things that I learn the next time around. Okay, and so today we're going to do part 1 of lipoproteins. It's going to be on the basics, and we'll just talk about their main function, what they're really known for in the medical world. And then in future episodes, we can look at other aspects of lipoproteins. So let's go. Okay, let's just start with what they're for. Essentially, as I said, again, in the medical world, they're just seen as a transport system, really. And it's a way to transport different substances, particularly fatty substances, lipids, around in the body. And that's because many of you will realize that fats and water just don't mix, right? They separate out into layers. And so it's a bit of a challenge to transport fats around in the body. And so we've developed this lipoprotein system to help us do that. So let's just look at what a lipoprotein is made of, the general structure. Let's start with that. We have a lipid part, the lipo, and then of course we have the protein part of it. And we can think of it first as an inner core where all the lipids are stored. And again, these are not soluble in water, and so they have to be hidden away from the plasma. So they're right inside and deep inside the lipoprotein in the core. And then this core is surrounded by a membrane, and it's a phospholipid membrane, just like your plasma membrane, except it only has one layer. So the plasma membrane at the cell surface is a bilayer, and most of us are aware of this. But here on the lipoprotein, you just have a monolayer, a single layer of phospholipids. And then within that membrane, of course, you have some free cholesterol to help with the shape and stability of that membrane. Okay, so we have free cholesterol there. The inner core is, fats like triglycerides or triacylglycerides. We could have some phospholipids in there, depending on the type of lipoprotein. We have some cholesterol esters. We have some fat-soluble vitamins and so forth packed in the inner core. And then we have this monolayer of phospholipid membrane studded with some free cholesterol. And then also at the surface, we have the protein part, and these are apolipoproteins. There are many different types of apolipoproteins, and what they do is they help to stabilize and solubilize the lipoprotein, okay? Because these proteins have parts of it that are soluble in water, and that is what makes them handy, and they can, get into the bloodstream. But they're also carrying the fatty substances inside, which are not soluble in water, and those are well protected from the plasma, all right? So the apolipoproteins help to stabilize the structure of the lipoprotein, and they also help solubilize the structure of the lipoprotein. The other thing they do is they're also for binding to receptors so that they can be taken into cells, right? The lipoproteins. So they're used for binding to receptors, and the apolipoproteins are often cofactors for different enzymes that are involved in lipid metabolism. So these apolipoproteins are quite important. And then associated with the lipoprotein would be other types of proteins and enzymes as well. Okay, so that's the general structure of, your generic lipoprotein. But we can divide up the lipoproteins into different classes. So we're going to start with the GI tract in the intestines, okay? And we're going to start with the import of fatty substances into your body, right? So if you think of it as taking in fatty substances from the diet exogenously into the body, then now we've got to go to the port, right? And pick up that delivery and then, deliver that cargo domestically in the body. So we have the exogenous dietary fats, mostly triacylglycerols or triglycerides that are taken into the intestinal cells. And then we're going to have to make a lipoprotein to transport them around. And these lipoproteins are called chylomicrons, chylomicrons. So chylomicrons are assembled in the intestinal mucosa, and the apolipoprotein associated with them would be B48. Okay, ApoB48, and there's one copy of that apolipoprotein per chylomicron. Now, the inner core of this chylomicron is going to be mostly triacylglycerols or triglycerides, okay? Same thing. So you're going to have mostly the triglycerides. You may have a little bit of cholesterol esters, but the bulk of it is going to be the triacylglycerols. Now, the ApoB41, this apolipoprotein is unique to chylomicrons. You don't find it in any other lipoprotein. So if you see an ApoB48, then you know that we're talking about the chylomicron, right? There are other apolipoproteins associated with the chylomicrons. This would be A1, ApoA2, also ApoA4. I think I'll briefly mention ApoA4 because I think it's interesting. It's synthesized in the intestines exclusively, and there's also one other place that you'll find ApoA4 made, and that is in the hypothalamus, the arcuate nucleus of the hypothalamus in the brain. And it's really for the sensation of satiety, all right, the central ApoA4. And what we've seen is they've done experiments where they gave central injections into the brain of antibodies to ApoA4 in mice. And when that happens, then the mice actually keep feeding. Now, normally mice are nocturnal, so they're awake and active, and they feed at night, and then they kind of go to bed in the daytime. But when you've given them these anti-ApoA4 antibodies in the brain, then they eat all the time. They even eat during the day when they normally don't feed at that time. So this ApoA4 has really an impact on satiety and appears to be under the influence of leptin. Now, one of the things I made myself promise in doing this episode, and made all kinds of notes here, is not to go down any rabbit holes. There are so many rabbit holes here, which is what's going to make it difficult to get straight through this episode. I don't want to dive into any of them. This is supposed to be a general introduction to lipoproteins, and then we'll have further episodes where we can kind of be a little bit more specific about different aspects of lipoproteins, all right? But I thought the ApoA4 was interesting because it's not only in the gut, but we also find it in the brain. So we have the chylomicrons formed, and they have their cargo of triglycerides, and they go into the lacteals, Lacteals. These are the end vessels of the lymphatic system, kind of akin to capillaries in the blood vessel system, right? We have the end vessels here in the lymphatic system, the lacteals, and so they are then going to enter the lacteals and enter the lymphatic drainage or system that way. And this is how they can circulate around the body. Now, eventually, though, the lymph is going to actually be dumped into the bloodstream as well, returned to the bloodstream. And it does this via the thoracic duct in the left subclavian vein. And at this point, then the lymph enters into the blood. And when this happens, those chylomicrons are going into the bloodstream at the same time, and they can now come into contact with HDL, which is another lipoprotein. We'll talk about it later on. But one thing you should know about HDL, the way I like to think about HDL is like a big sister. I don't have a big sister. I have two younger brothers. I always thought it would be nice to have a big sister, and that way you can borrow from her wardrobe, right? So you don't have to have all the best clothes, but you can always borrow your big sister's clothes and then return them. So it kind of expands your repertoire in terms of your clothing, right? So unfortunately, my brother's wardrobes did not appeal to me, so I couldn't borrow from them. But you can think of HDL as a big sister, and that's constantly lending out parts of her wardrobe. So here, when the chylomicrons go into the bloodstream, they can acquire ApoC2 and also ApoE from HDL. So they get these apolipoproteins from HDL. Now, I told you that the whole purpose is to transport the fats that we picked up in the digestive tract and then bring them to various parts of the body. So now we have to be able to unload the cargo, right? So when we get to different tissue, like fat tissue, like skeletal muscle or heart muscle, cardiac muscle, then we have to be able to unload those fats such that the tissues can use the fats as fuel. And to do that, we have a protein, an enzyme called lipoprotein lipase. And this lipoprotein lipase, what it does is it breaks the triacylglycerols into fatty acids and glycerol. So it breaks them into their component parts. Now, LPL, or lipoprotein lipase, this is actually made in the tissues, right? Like the parenchyma of adipose tissue, and also skeletal or cardiac muscles, right? And what happens is that they're made in the endoplasmic reticulum of those cells, and then they're kind of exocytosed and brought outside the cell, where they bind to heparan sulfate proteoglycans. Yay! Now that we know about those gags that are pretty much everywhere, right? And they're all on the surface of every cell. So as the LPL is secreted out, then it can bind to the HSPGs, or the proteoglycans, and then it's picked up there by a protein and then transported to endothelial cells lining the capillaries, okay? So that's how, they're not actually made, this LPL is not actually made in the endothelial cells, it's made in the parenchyma of the tissues, and then excreted out and then carried by a protein to those endothelial cells. Now, once we get into the endothelial cell, then it can get to the luminal side, which is the side of the cells that face the inside of the blood vessel where the blood is flowing. And what this LPL does is, in the presence of phospholipids, right, which it has on, which the lipoproteins have, these chylomicrons have that membrane of phospholipids, right? And in the presence of ApoC2, which the chylomicron acquired from big sister HDL, you'll remember, then we can now break up those triacylglycerols into their components of glycerol and fatty acids. So we have the fatty acids being picked up by cells to use as fuel, or if it's adipose tissue, it could be used for storage. And then the glycerol goes into the bloodstream, eventually ends up in the liver, and it can go through gluconeogenesis, and we can make glucose that way. All right, so that's how we unload the chylomicron with the help of LPL, or lipoprotein lipase. Now, when you have done this process, you basically kind of digested the triacylglycerols, right, and broken them down into fatty acids and glycerol. Then a substantial portion of the phospholipids on the chylomicron, the ApoA and ApoC, are transferred to HDL. So we kind of return the ApoA parts and the ApoC, and some of the phospholipids, we kind of give it back to HDL. Now, once we have transferred ApoC2, remember, we needed ApoC2 to activate LPL. So once you have given C2 to HDL, then lipoprotein lipase can no longer do its work, right? So we stop the action of LPL at that point. I briefly just want to mention also these proteins that are called angiopoietin-like proteins, right? And these are part of a big family that are structurally similar to angiopoietin, which is used for angiogenesis, making blood vessels and so forth. They're structurally similar, but they have different functions from angiopoietin. And so they're called angiopoietin-like proteins, all right? And we have, angiopoietin-like proteins 3, 4, and 8. I don't want to go down that rabbit hole, but I will just say that they also help regulate the activity of LPL. Now, in the end, what you want is you want to pick up the nutrients, in this case fats, right? And then when you've got food, you've just eaten, then we want to store the fat in the fat tissue. And so then we're going to have lipoprotein lipase activity highest in adipose tissue and lowest in cardiac or skeletal muscle, because we just ate and we want to focus on storing some of that energy. But when we're in a fasted state, then we want to have more LPL activity in the skeletal muscle and in the cardiac muscle so that we break down the triglycerides and access the fatty acids and also the glycerol for fuel, right? And we want low LPL activity in the adipose tissue because we really don't want to store any more of the triacylglycerides in a fasted state. We need to actually be accessing some of this for the skeletal muscle and the cardiac muscle, okay? So there's differential activity in the tissue depending on fasted or postprandial state of this LPL, and this is under the guidance of those angiopoietin-like proteins, okay? So I'll just leave it at that and not go down that rabbit hole. Okay, so now we've gotten rid of a lot of the triacylglycerides, and the chylomicrons now have less of the triglycerides in the core. They have cholesterol esters, they have some, maybe a little bit of cholesterol as well. They still have a little bit of the triglycerides, but much less than before. And they also have ApoE, and remember, they have that ApoB48, and they are now transported back to the liver and taken up via the LDL receptor in the liver, and they can also be taken up by those heparan sulfate proteoglycans, right? Remember in the glycocalyx episode, I talked about that too, and how these HSPGs are actually receptors for triglyceride-rich lipoproteins, and you know, some of these chylomicron remnants still have a fair amount of the triacylglycerols in them, so they can be taken in to the liver that way. All right, so that was from the dietary fats, right? That's how we disposed of the dietary fats. Now let's turn our attention to endogenous fats, right? So these are fats or triglycerides that you make in your own body, primarily in the liver. So with endogenous fats, right, the liver is going to be making a lipoprotein called VLDL, or very low density lipoprotein, and it's going to package mostly the triglycerides, again, a little bit of cholesterol, some cholesterol esters in together in the center, the core part of the lipoprotein. And associated with VLDL is the apolipoprotein B100, okay? So with the chylomicrons, you'll remember it was B48, and now we're talking about ApoB100, and this will make the VLDL. Once that lipoprotein gets into the bloodstream, it's going to meet up with HDL again, borrow something from the wardrobe, and we're going to acquire ApoC2, C3, also ApoE from the HDL. And now we're going to go in the bloodstream, get to different tissues, and there again we will release this fatty acid and glycerol in the adipose tissue, in the muscle, and so forth via LPL, or lipoprotein lipase. Okay, so there's a lot of similarities between the chylomicron and the VLDL. They are triglyceride rich, and the difference would be that we have ApoB48 on the chylomicron, but we have ApoB100 on the VLDL. Now, again, as we are releasing the fatty acids, then we're going to lose some of the triglycerides in the VLDL, and we're going to start to change the shape and size of that VLDL lipoprotein, and as a result, we're going to lose ApoC2, right? And now that VLDL becomes something called IDL. IDL is intermediate density lipoprotein. So IDL also has that B100, one copy of B100, right? Because it came from VLDL. So we just lose some of the triglycerides, and now with a change in size and the loss of ApoC2, we now become IDL. We have the B100, but we also have some ApoE. Remember, that's still on the IDL. And so that IDL can be taken up by the LDL receptor. And, that happens in the liver. Now, I just want to mention with regards to the LDL receptor that it is generally known as the ApoB, ApoE receptor because it recognizes ApoB and it also recognizes ApoE. So with ApoE, it's going to facilitate the uptake of the lipoprotein by the LDL receptor. If you just have ApoB, well, the LDL receptor will still take in the lipoprotein, but not as well as if you also have ApoE. So the presence of ApoE on the lipoprotein really facilitates its uptake by the LDL receptor, okay? So eventually that IDL with still a little bit of triglycerides around, right? It gets some of that released as fatty acids and glycerol. We lose some of the triglycerides, and we also return the ApoE to HDL. Okay, we borrowed it from HDL to begin with. So now we return the ApoE, and that's when we form LDL, or low density lipoprotein. Okay, so you can see that LDL is really a result of VLDL metabolism because it comes from VLDL in the end, right? And LDL is, it has the apolipoprotein B100 still, but doesn't have ApoE. Remember, that was returned back to HDL. So we just have the B100. So as a result, it can still be recognized by the LDL receptor, but not as well, right? If it had the ApoE still present, then it would have been a lot easier to be taken in by the LDL receptor. But now we just have the ApoB, okay? So it still will be recognized and taken in by the LDL receptor, but not as well. All right. So the LDL mostly now has cholesterol esters in the core. That's going to be the main cargo because remember, we've already released and used up most of the triglycerides, right, that were in the VLDL and some were in the LDL as well. We've already kind of processed them, and now we're left with the remainder, and the remainder is mostly cholesterol esters, some free cholesterol as well in the LDL. So when you think of LDL, their cargo is mainly going to be cholesterol esters and cholesterol. Now, these cholesterol esters can also be used by cells because after all, cholesterol is very important for formation of membranes. We're going to make steroid hormones with them. So it's a very useful substance. So we can traffic the cholesterol around, right? And what we do is we can take out this cholesterol ester, and we can, inside the cell, take up some of that cholesterol ester, but we can hydrolyze it, and we're going to make cholesterol, free cholesterol, that we can use, let's say, in the plasma membrane, right? And any excess cholesterol that we have in the cell, we can re-esterify it, okay? In other words, we're going to link that cholesterol with fatty acids. When we talk about cholesterol esters, by the way, we mean that it's just cholesterol linked to fatty acids, okay? So we can now re-esterify the cholesterol, and this is through an enzyme called SOAT2, SOAT, all in caps, 2, and that's steryl O-acyltransferase 2. It used to be called ACAT2, but that made it a little bit confusing because there was another ACAT2 enzyme. And so just to clear the confusion, it's now called SOAT2. And this SOAT2 just takes any free cholesterol in the cell and reesterifies it, reattaches it to a fatty acid. And once we have now a cholesterol ester, we can store the cholesterol in that form in the cell. Okay, so the LDL is taken in, as I said, by the LDL receptor. This LDL receptor has different parts to it. The extracellular part, or the extracellular domain, that's the part that binds to LDL. Then you have a transmembrane part. And then internally, basically the LDL receptors tend to cluster together in what we call coated pits. Okay, and this is going to be important in the uptake of LDL. So essentially, the LDL is bound to the LDL receptor. And sometimes also we have PCSK9 there, remember from the glycocalyx episode. That is actually bound to the proteoglycans, heparan sulfate proteoglycans, which also now can present this complex to the LDL receptor. Okay, so we take in the LDL and some of this PCSK9 maybe, right? And when we take it in, then it is taken into these coated pits as an endosome. So it's a little compartment now that is taken into the cell. So this endosome, this compartment, then becomes acidified. And once you acidify it, this has the effect of dissociating the LDL from the LDL receptor. Okay, so we free up the receptor. The receptor can then go back to the plasma membrane and be recycled. Okay, and then the LDL can be in that endosome fused to a lysosome, and then we break it down even further. All right. If, however, that LDL receptor is bound to PCSK9, as we talked about in the glycocalyx episode, then we're not going to allow the LDL receptor to go back and to the cell membrane and be recycled. So now we have less LDL receptors on the surface of the cell, and this means then we have less ability to take in LDL. We have more circulating LDL in the bloodstream. Okay, just to finish it up, in the lysosome with the LDL that's degraded, that cholesterol now is released as free cholesterol, right, broken down into free cholesterol. That can be used by the cell for its cell membrane, for example. But if we find that, okay, we don't need it right now, then in the cell, we can re-esterify it with SOT2, remember, the steryl O acyltransferase 2 enzyme, and we can now add fatty acids to that cholesterol and store it in the cell that way, okay? So what you can see then is that when you take in a lot of cholesterol through the LDL receptor, then the levels of cholesterol in the cell go up. This sends a message to the cell, and so we're going to now say, well, okay, we got plenty of cholesterol. We don't need to bring in any more. So we're not going to synthesize more LDL receptor. Okay, why? Because we already got plenty of LDL. We don't need to bring in any more. And the other thing is, we'll also not make any more cholesterol. Okay, because we have plenty of that. So you can see that there is a feedback loop. Okay, so when you have increased cholesterol levels in the cell, this sends a signal to not make more LDL receptor and to not make more cholesterol, so we don't keep increasing the levels of cholesterol in the cell. All right, and just for completion, there are other receptors that are involved that can bring in lipoproteins like LDL. We have LRP. This is LDL receptor related proteins. They're part of the same family, and they have diverse biological functions, but they can also act as receptors for lipoproteins. So one of them, for example, LRP1, That's an ApoE receptor, but it can also bind to very many different things, like over 40 ligands. So you can see it can bind to lipoproteins, extracellular matrix proteins, cytokines, and growth factors. So it can bind to a whole number of things, but amongst them, it can also bind to lipoproteins, okay? And then other receptors would be things like scavenger receptors. These we can find in immune cells. And the thing about scavenger receptors that I think is important to remember is that it doesn't have the same sort of negative feedback that the LDL receptor has, okay? So when a cell like a macrophage cell, one of my favorite cells in the body, right? And we're going to talk about macrophages in relation to atherosclerosis and other important disease processes in the body. Just a quick plug here. I have a video out. It's called the Magical Mystery Macrophage Tour, and that's an overview survey intro to macrophages. So if you've got a chance on YouTube, go watch that, the Magical Mystery Macrophage Tour, because when I talk about macrophages, I will be kind of jumping off of that. I won't cover the same material that I did in that video. I'll just be talking about different aspects because there are just too many things to talk about in macrophages, okay? But macrophages, for example, have these scavenger receptors. And as I said, there's no feedback regulation, so not a negative feedback regulation. In fact, actually, when they take in cholesterol, the more cholesterol it senses internally in the cell, it's actually going to upregulate more of these scavenger receptors. And that's not a good thing because now we're just going to bring in more cholesterol, and we already have a lot of cholesterol. We keep bringing that in, and over time that's going to cause problems, right? So that's a distinction between some of these scavenger receptors and the LDL receptor, for example. Okay, so we branched off not really. I did try to stay on the main track, try not to go down rabbit holes. We're going to now just talk about HDL. Now I'm going to do probably a whole episode just on HDL alone, but let's just do the basics here, okay? So HDL, everybody talks about it as the good cholesterol. It's the lipoprotein that basically helps bring cholesterol from the tissue back to the liver. And there in the liver, we can convert the cholesterol to bile acids and then excrete it. Okay, so that's how we can get rid of cholesterol, which is why people see HDL as the good guy in the story. And it's able to do this reverse cholesterol transport where it takes cholesterol from tissue and brings it back to the liver. You know, which technically LDL brings cholesterol back to the liver, but okay. All right. Anyway, HDL is also seen as anti-inflammatory. It's an antioxidant in some ways, has some vasodilatory effects, so it can be good for your blood vessels. And particular species of HDLs have been shown to be antithrombotic and anti-apoptotic. This is specifically the HDL3. And, you know, there are other functions of HDL besides this pure transport. But again, I'm not going to go down the rabbit hole. We'll do a whole episode on HDL at some point. Let's just look at the basic plan here. All right. So HDL, it begins or is synthesized initially in the liver and also the small intestines. Okay. And it begins with ApoA1. Okay. And over time, it starts to pick up other proteins. So it picks up ApoC1, ApoC2, and it picks up cholesterol. It also picks up ApoD, EF, MO, and lots of other enzymes. Okay, I already told you it's like that big sister that is always lending out, pieces of wardrobe. So it's always known as a circulating store of ApoC1, C2, and also ApoE. Okay, so it can be useful that way. But really, 70% of the total protein mass of HDL is made up of ApoA1. And in addition to that, we have with HDL, many other proteins, over 300 enzymes that are not associated with lipid transport. Okay, so it has other functions there. All right, so we have HDL. Some of the enzymes that are important with HDL, one of them is LCAT, lecithin cholesterol ester transferase. And what this does is it actually, and you find LCAT in both HDL and LDL, but what it does is it's a way to esterify extracellular cholesterol. So it basically, if the lipoprotein acquires free cholesterol at the membrane, then we can convert it using this LCAT to cholesterol ester. And once we make the ester form, we attach it to a fatty acid, we can now sequester this cholesterol ester in the core of the lipoprotein. So essentially, we're moving the cholesterol from the surface to the inner core of the protein with this LCAT. Okay? So it's made in the liver, and it's very useful because if we encounter cholesterol anywhere, we can take it up, esterify it, add fatty acid to it, and then bring it into the inner core. The other enzyme is cholesterol ester transfer protein, or CETP, and I kind of think of CETP like a trader type of protein because it basically helps transfer cholesterol esters between lipoproteins, right? So with CETP, then HDL can exchange cholesterol esters usually for triglycerides. Okay, so we can go around and we can trade triglycerides and cholesterol esters, or vice versa, with CETP. Right. So, for example, you have a chylomicron or VLDL, and that might give up some triacylglycerols to the HDL in exchange for some cholesterol esters. Okay, or it can also give some cholesterol esters to HDL and have the HDL give some of the triglycerides to the VLDL or chylomicrons. Okay, so that's another useful enzyme to have around, or protein to have around. All right, so let's talk about how HDL actually takes the cholesterol from tissues back to the liver. It does so with our friends, again, the macrophages. So these immune cells are really important because they are the ones that take up cholesterol from tissue, right? And they take them they phagocytose, or they kind of swallow up the cholesterol. And then they are able to take this cholesterol and transfer it to HDL via ApoA1, okay, through a protein called ATP binding cassette transfer protein, ABCA1 is how we refer to this transfer protein, okay? And it's A1 because it relies on ApoA1. Very important here, all right? So with ApoA1 on HDL, then ABCA1 from the macrophages can transfer cholesterol to the HDL. And now the HDL, baby HDL, which mostly has just ApoA1, starts to accumulate cholesterol, and we esterify that cholesterol and we bring the cholesterol into the core, and now this baby HDL, which was discoidal initially in shape, now begins to get spherical, round, and fat, right? And over time, as it accumulates more cholesterol and other proteins, it becomes a mature HDL. Okay, that's most of the way it acquires cholesterol. It can also take cholesterol directly from some membranes, for example, of cells. So 20% of the cholesterol it acquires is just directly from cells, right? And then it can take, again, that cholesterol, esterify it, and sequester it using another transfer protein, ABCG1. Okay, so this is how it eventually takes up cholesterol in peripheral tissues. Now the HDL goes back to the liver. Now the receptor for HDL is a scavenger receptor called SRB1. SRB1. So this is what actually binds with HDL. But even though it binds at the membrane, it's not actually internalized, okay? What happens is it binds, and then we have these special parts of the lipid membrane called caveoli. And these caveoli are like lipid rafts. They're usually involved in a lot of cell signaling and so forth. But when HDL, with its cholesterol, is bound to SRB1 at the cell membrane, these caveoli take in the cholesterol esters, but they leave the HDL and the SRB1 at the membrane surface, okay, at the plasma membrane. So the thing is, the HDL also with CETP, remember that transfer protein, is kind of doing a lot of trading of triglycerides and cholesterol esters with VLDLs and IDLs and chylomicrons and LDLs in the circulation as well. Okay, so and eventually those lipoproteins get back to the proteins, get back to the liver. So that's another way we can technically do this reverse cholesterol transport and get that cholesterol back to the liver. Right. However, when that happens, a lot of times when we're exchanging substances or cargo between, let's say, VLDL and an HDL, if the cholesterol ester is being given to the VLDL and in exchange, the HDL is acquiring triglycerides, right? Then you're going to have an HDL that's kind of filled with triglycerides. And eventually, when that HDL makes its way back to the liver has an enzyme called hepatic lipase. And hepatic lipase will break down the triglycerides that are now in the HDL. Normally, it doesn't have a lot of triglycerides, but if it exchanged it via CETP with, let's say, a VLDL in the circulation, and then now it's got more triglycerides in it, and eventually when it makes its way back to the liver, it's laden with triglycerides, but that's okay because we have hepatic lipase, which can break down the triglycerides, right? But the problem with that is, now that we've broken down the triglycerides in the HDL, okay, so now we have a very different type of HDL. Its shape is very different, okay, because the triglycerides took up a lot of space. Now that we've hydrolyzed them, right, now the remainder of the HDL is very small and dense, okay, and that shape is very unstable, and as a result, ApoA1 tends to dissociate from it, okay, and when we do that, we lose the ApoA1. Guess what? We're not able to do any more reverse cholesterol transport, because remember, for the macrophages to transfer the cholesterol to HDL, it had to have the involvement of ApoA1, right, with the A1 protein. Okay, so no A1, no reverse cholesterol transport. So you can see that, it's very helpful in getting the cholesterol back, but in some cases, we might not be able to facilitate reverse cholesterol transport. Okay, very quickly, I just want to go over another lipoprotein. This is LP little a, and the way it's written is capital L small p brackets small a, okay? And it's referred to as LP little a. And this is LDL essentially linked to apo little a. Okay, that's the apolipoprotein little a, right? So we have LDL, and it has this apo little a with it. And now it's lipoprotein little a, or LP little a. It also has still the B100, because after all, it is still LDL. Okay? And this LP little a, it's made in the liver, has a half-life of 3 to 4 days. And, this is a bit of an enigma to most people. Nobody really knows exactly what it does. But what we do know is that it's structurally very similar to plasminogen. Okay, now it has these structural units in it called Kringle units, and they're called Kringle units because they kind of look like pretzels or Danish Kringles, right? So it just structurally looks that way, so they were named Kringle units. And there are many subclasses, there are 10 subclasses of these Kringle domains. In LP little a, we have single copy of the Kringle domains 1 and 3 all the way through 10, all single copies. Kringle domain 2 is different. It has variable repeats. So as a result, you're going to have different sizes of this LP little a. So when you have low molecular weight LP little a, then you have actually high levels of this in the plasma. And with the high molecular weight isoforms of LP little a, you have low plasma LP little a levels. Okay, and those levels affect the function of the LP little a. One thing you should know is the LP little a can be oxidized very easily. It can also be glycated easily. So as you know, with glycation, that's never good because you're going to increase inflammation. We know there's a strong correlation between levels of high plasma levels of LP little a and atherosclerosis, coronary artery disease, which is why people have been very interested in it. As I said, it's very similar to plasminogen, and it competitively inhibits the binding of plasminogen to its receptor on endothelial cells or to fibrinogen or fibrin. Okay, so plasminogen is, when it's activated, becomes something called plasmin. And this plasmin is very useful because it helps break down fibrin, it breaks down clots. Okay, so any clots that are around are broken down and dissolved by plasmin, but plasmin is actually from plasminogen. The plasminogen is activated when we get plasmin, and that plasmin now can break down the clot. But remember, the LP little a, structurally quite similar to plasminogen, will not allow the binding of plasminogen, and therefore we're going to interfere with breaking down of clots. And if you have the low molecular weight LP little a, you have more of this fibrin binding capacity and less dissolving of the clot, right? So the net result is you have a decreased ability to dissolve clots and maybe a more thrombotic environment. Also stimulates the growth of vascular smooth muscle tissue cells, which, we can see would be important in atherosclerosis. I'm just going to throw that in there just so we have it, in this general picture. I'm not going to go down that rabbit hole, but there certainly are rabbit holes in association with LP little a as well. Okay, so now we talked about the different classes of lipoproteins, how they circulate, the different apolipoproteins that are involved, that allow, and the enzymes involved to help them do different functions and help them transport lipids, fats, triglycerides, cholesterol around in the body. Okay, so some of you are aware that we can actually subfractionate the LDLs and look at the different species of LDLs, all right? So the way a lot of times the lipoproteins are described or taught, they're taught as these distinct classes, and you have the VLDL, and now you have the IDL, and now you have the LDL. But the truth is that there's quite a big range, even within each class of lipoproteins, in terms of size and shape, and also the proteins that are associated with those lipoproteins. So it reminds me of a time when I did a medical elective, again as a medical student. This time I was in Kathmandu, Nepal. And they have these tempos there. And tempos are essentially these three-wheeled scooters, I think, right? And it's made, it looks like a little minivan, but it's essentially a three-wheeled scooter. And it can take maybe about 8-10 people in it, right? So it's a mini scooter van. And it was a very convenient way to get around the city, right? So they'd have these tempos. Now, recently I was trying to take the T, which is our subway system in the Northeast in Boston, right? And when the T got full, the conductor said, "All right, this train is full. No more passengers coming in. You can only go out." And they wouldn't take any more people in. So they were very regulated that way as to the number of people they would take in. It was very different with tempos, okay? Tempos, maybe it could fit 8 to 10 people, but oh, you got 2 more there? Yeah, come on in. You got a kid? Come on, it's okay. Oh, you want to bring your goat here? Oh, sure, why not? You got a bag? Then throw it upstairs, right? Throw it on top of the tempo. Can we take one more? Listen, can you hang on by fingernails? Yeah, you only need 2 fingernails. If you can hang on, we can take you, right? And so it was just a lot more freewheeling. And, you know, even though the tempo was meant for 8 to 10 people, sometimes you'd have 12, plus a few other animals and other luggage here and there, right? And your face would be squished up against someone's back or something, right? And somehow we just got to where we needed to, and, you know, mostly in a safe manner, right? Okay, so that's kind of the same with the lipoproteins, because, you know, a VLDL, well, you have bigger VLDLs, you have smaller VLDLs, some have more ApoEs, some, you know, have less, right? So they all have only one of the B100, but, you know, the other apolipoproteins, there may be multiple copies, some more, some less, right? So there's a lot of flexibility even within each class. Okay, so I think one of the big things to take away is to realize that we're not really talking about one specific lipoprotein in a certain class, but there's always a range of sizes, shapes, associated proteins, enzymes, and so forth per lipoprotein. A lot more flexibility that way. Okay, so when we're talking about the LDLs, for example, people started to note that really we have a range of these LDLs, and it's really the small, dense LDLs that are much more atherogenic, okay? Much more involved in causing or associated with atherosclerosis. So people started saying, well, we should look at what type of LDLs you have, and if they're small, dense, then yeah, your risk for atherosclerosis is a lot higher. But if they're the large, buoyant ones, then, you know, it's neutral, okay? You're pretty good. Don't worry about it, right? So everybody now walks around, if they have a subfractionation, they'll go, well, you know, I have high particle counts, but you know, most of it is the large buoyant type, and, you know, or someone else may have a lot more of the small dense types. So then the question becomes, so the small dense LDLs, where do they come from, right? So I've asked people that, and generally never got an answer. So had to do a bit of digging, and over the years, read a little bit, and it turns out it's pretty interesting. So remember that these lipoproteins, like the tempos, they have variability in size, and they're a bit more freewheeling than they are depicted. So there's a constant exchange of different cargo between them. Also, if someone starts off with a lot of triglycerides, so if someone has a high carb intake, right, and they have a lot of triglycerides on board in their body, right? So now when we have the VLDLs, these VLDLs are bigger and they have a lot of triglycerides in them, okay? And when these big, triglyceride-rich lipoproteins, the VLDLs, right, are eventually kind of processed and they become LDLs, or they exchange, different cargo, and we get to LDLs that have higher content of triglycerides, right, than normal. You have these bloated LDLs. They have a lot more triglycerides than you normally would see. So those triglycerides in the LDL, they are processed by hepatic lipase again when we get back to the liver, which is not a bad thing, right? So now we can actually break down the triglycerides in the LDLs. Right? Normally, like I said, you don't have a lot, but someone who is doing a lot of carbs and they have high triglycerides, yeah, you're going to have, a lot more of the triglycerides floating around. And so you might have LDLs that now have more triglycerides than normally, right? And the hepatic lipase is very useful because it's going to break down those triglycerides in the liver. But when you do that, now that you have removed the cargo of big triglycerides, right? What are you left with? You have less cholesterol because you had more triglycerides in your cargo, even though you're an LDL, okay? And now you also, in terms of the ratio between proteins and lipids and fats, right? You have more of the protein elements, so you're denser. And these are the small, dense LDLs, right? Their shape is different, and, again, the density is different, okay? Because they started off by having more triglycerides in them, and eventually when we break down the triglycerides via hepatic lipase in the liver, now we are left with some of these kind of misshapen, small, dense LDLs. So that's where we think the small, dense LDLs come from. Again, it's kind of trickled down from the VLDLs, okay? So that's one piece. And the other piece when we talk about lipoproteins is nowadays, it used to be that everybody would say, oh, cholesterol causes atherosclerosis, right? And now I looked recently, and in the BU curriculum for med students, they very carefully said it's actually oxidized LDLs. So we have a shift from cholesterol. So now the curriculum, I looked at it just very recently, it said oxidized LDLs. And you hear a lot of that. People going around, well, it's the oxidized LDLs, right? I'm a very basic person, right? So I ask very basic questions. I go, well, okay, oxidized LDLs, oh, okay. Excuse me, so what's oxidized? Huh? Yeah, I mean, you said oxidized LDLs, right? So like LDL, it's a lipoprotein. Remember, you have the core, you have the phospholipid, you have the cholesterol, you have the protein. So what is oxidized? I told you I'm very basic, I'm trying to understand this. And I asked a lot of people. So at this point in the episode, if we were to have a musical interlude, we would cue the Simon and Garfunkel song, The Sound of silence. What do you mean, what's oxidized? Yeah, I just want to know what's oxidized, because oxidized LDL, that's the bad guy, right? That's what's, causing atherosclerosis. So what's oxidized? And yeah, asked a lot of people, didn't get an answer. Some people ventured, cholesterol. I'm like, really? Just cholesterol? Because we have cholesterol esters, we have phospholipids, a lot of fatty acids, we have the proteins, the apolipoproteins, and it's only specifically the cholesterol that's going to be oxidized, really? So I had to look it up. Turns out any and all of those things can be oxidized or modified, all right? So we have the lipid part. So we have fatty acid oxidation products. And so remember, the phospholipids have fatty acids, cholesterol esters have fatty acids attached to them, right? So these can be oxidized and form fatty acid peroxides and hydroxides. We have prostaglandin-like products and aldehydes that can be formed from the oxidation of these fatty acids. We also have lipid-derived products, and these are like lysophosphatidylcholine, cholesterol oxidation products, and other lipids that can be modified. We can also have protein oxidation products, because after all, we got all those apolipoproteins and enzymes and so forth on lipoproteins, so we could have modification of those components. We can also change certain characteristics of the lipoprotein, so we change the buoyant density. We can also change the charge, right? So there are many ways. When we talk about oxidized LDL, it isn't one thing. It's really any LDL that is modified, warped, deformed in some way. For example, desilylation, which is removal of sialic acid groups, right, from the lipoprotein, that's actually not a good thing. So the sialic acid, again, our GAGs, right, all that glycobiology here. But if you remove those sialic acid groups from the lipoprotein, right, that's actually associated with higher incidence of atherosclerosis. Okay, so we can modify these sugar groups. We can modify the charge on the lipoprotein. Any time you modify it, we call that oxidized LDL, it seems. Okay, doesn't have to be an oxidation reaction exactly, but any kind of modification. Because once you modify the LDL, and here's the important part, you modify it so your body goes, I don't recognize that. That's strange. That's a problem. Okay, that is not normal LDL. And as a result of that, your immune cells are going to go, whoa, we have a problem, we have an intruder. And we set up an inflammatory reaction. So it's really that modification such that the body recognizes it as a problem, and now we set up an inflammatory response, and that is what is going to, kind of upregulate the whole process of atherosclerosis. Okay? So I know I rushed through it's always like that when I have challenges in my schedule, but I hope I got in most of the main points. And like I said, we can dive a little bit deeper now into lipoproteins now that we got the basics out of the way. The main things that we talked about, so time for a wrap up, right? We went into the structure of a lipoprotein and how they're made up of the inner core cargo of fats and lipids, and then we have the monolayer phospholipids at the surface, the membrane, and that also has some free cholesterol associated with it. And we also have those apolipoproteins and other enzymes and proteins that are associated with the lipoprotein. And its main function here today is in the transport of fats and lipids in the body, right? And then we talked about different classes. So we started in the gut, and we have the chylomicrons forming there. They have the main lipoprotein that is associated with it is B48. It's unique to chylomicrons. And it also has other apolipoproteins. Interestingly, A4 is found in chylomicrons, but also made in the hypothalamus, and has an effect on satiety and feeding. Once the chylomicron gets in the lymph and eventually gets into the bloodstream, then it acquires other lipoproteins, ApoC and also E from HDL, and via lipoprotein lipase, we can deliver some of the fats, the triglycerides that are in the chylomicrons to different tissue, and those remnants eventually make their way back to the liver. We also have endogenous triglycerides that we make in the body, and the liver packages them in VLDLs. And this is associated with the apolipoprotein B100. And again, when it gets into the bloodstream, we get ApoC, ApoE from HDL again. We can carry the triglycerides to different tissues and deliver them there, where they're broken down into fatty acids and glycerol. And then now we are mostly having cholesterol, still some triglycerides in them, but we also lose ApoC2, and now we become intermediate density lipoproteins. Those are eventually, again, going to lose more triglycerides, right? And they lose the ApoE, and they become LDL. And these low density lipoproteins are carrying mostly cholesterol esters. They make their way back to the liver. They're taken in via the LDL receptor. And as a result of increased cholesterol in cells, normally we would decrease the formation of more LDL receptor and the formation of more cholesterol, and that way we control the level of cholesterol within the cell. But as we decrease the LDL receptor, we also now have more circulating LDL, okay? In addition, if we have PCSK9 associated with the LDL receptor, then it prevents the receptor from recycling to the cell membrane. And again, we have less receptor at the membrane and therefore more circulating LDL. Then we talked about HDL and how it does this reverse cholesterol transport. And it does this by acquiring the cholesterol from macrophages, and this requires ApoA1, and it eventually takes this cholesterol back to the liver, where it's taken in by the scavenger receptors. And then, the other thing it can do to, facilitate cholesterol getting back to the liver is via the cholesterol ester transfer protein. It can start exchanging with other lipoproteins, so it can take in more cholesterol from those lipoproteins in exchange for triglycerides. However, we can also take in more triglycerides and give up some cholesterol esters to those other lipoproteins, and they eventually make their way back to the liver. Now, if an HDL does that and it's taken a lot of triglycerides, eventually when it gets back to the liver, that triglyceride content can be hydrolyzed by hepatic lipase, but this means that once it does that, now you have an HDL that is kind of misshapen, unstable, a lot smaller. And as a result, it loses its ApoA1, and then without the A1, you can't actually do the reverse cholesterol transport via the macrophages, okay? LDL, we also talked about how the LDL, the small dense LDLs are formed. So if we have a lot of triglyceride content in the LDLs, eventually when they get back to the liver, they too are processed via hepatic lipase. And now once we have gotten rid of the triglycerides, you have LDL that is misshapen, and it's a lot smaller and denser. And as a result, this is a signal to your body's immune system that there's something wrong, and we set up an inflammatory response. And finally, we looked at what is oxidized in LDL when we say oxidized LDL, and essentially anything is modified in oxidized LDL. And once you have modification of any of its parts, whether it's the lipid components, part of the membrane, part of the proteins, the lipoproteins, right? You have, again, these modified LDLs, and they signal to the immune system that there's something wrong, and we set up an inflammatory response. In addition, the small dense LDLs are at risk, high risk of being modified as well, because they're already misshapen, they're already abnormal, and then they can be further modified quite easily. And this can, again, cause more of an inflammatory response. Okay, so that was a whirlwind tour on our tempo through lipoprotein transport of fats. Okay, again, just one particular aspect of lipoproteins. I'd certainly like to do at least another episode on lipoproteins, but looking at different aspects, okay? But at least for today, we just covered that. I hope you found it helpful. Keep your questions coming. I love to hear from you. Check out my website, vivianlohmd.com, VYVYANELOHMD.com, for the schedule for the live stream events. And maybe I'll see you there if you have questions, or you just want to share parts of your metabolic health journey. I'd love to see you there. But for now, signing out from VLMD Rounds, I'm Dr. Vivian Loh, and I sing the body electric. Thank you. Bye.